people, when they researched how to bypass this, they're looking for generic methods to bypass like heap cookies. And the whole point of the protection was that it defeats all the generic methods. And it's easy to see that there won't be a generic method for defeating heap cookies and unlinked checks. And we can go over a little bit here what we're talking about. XP Service Pack 2 was the first OS from Microsoft where they introduced this, in my knowledge. And you can just see a little little pseudocode here. B-link means backwards link, F-link means forwards link. And in pseudocode, you can see the link list getting unlinked, and they do a check to make sure that everything is copacetic before they proceed, which foils are right for. And obviously, this is another beautiful graph. So the heap data also has, in the low fragmentation heap at least, has sort of checksums and various other protections that you're going through. In addition to being a bit more complex, it's also going to have a bit more reliable protection mechanisms. Clearly we've been looking heavily at Vista, and the newest immunity debugger that you download now, or the 1.2 version, will be able to decode the Vista heap structures and memory. And you can get a full Python readout of exactly how we do that, because everything is maybe not capital O, capital S open source, but at least viewable for you. And certainly, I think the version coming out this month it's better than WinDebug's tool for the same purpose. And likewise, if you overflow the check and then they free the object and do collection, they can tell that you've modified it, which is not good. There is obviously, if you look at the general size of the problem, they have a checksum, you've corrupted it. You can defeat that by having a memory disclosure vulnerability first. And you'll start seeing hackers combine a lot of vulnerabilities to do that. But regardless, pretending we can't do that, we want to defeat the following bevy of things. And the thing that's not listed on here is the Pete and the compiler and the many consultants that have been brought into Microsoft to squash the bugs individually, and all the other sort of things like the prefast and prefix and all that other stuff. So those are sort of in the same boat. We want to solve all the problems by finding bugs they can't, and exploiting bugs they think are unexploitable or that we are reduced to scourging for. So we include here a list of sort of references to other heap papers that you can read. And our conclusion based on these heap papers is that there is no generic bypass. So you can spend a lot of time analyzing the data structures and the algorithms, and you'll still come to the conclusion that it's really not that hard to prevent the write for from happening. And as Sinan says, who's one of our other researchers, he says that he can make a strawberry pudding with that many prerequisites. Which he means like, yeah, okay, if you have the following data structures and the following craziness, you get a write for because you know the data structures are the same. He's like, that's never going to happen. We need a better way. So what we do is we have a methodology that reliably generates application-specific write fors from heap corruption vulnerabilities. And all this good stuff is in Immunity Debugger right now, but maybe it's hard to use. That's the way it is. And you'll know that many of the good heap overflows have been very strictly controlling the heap in the past 5 years or whatever. You'll see, I know we have a list of the ones we've done, or that Nico realistically did. And so we come to the you can strictly control the heap, and then what is our question? And here's some examples. We use the spooler exploit against 2000, and you do like a multiple write fors to write a shellcode into memory, and then you jump to that shellcode after corrupting a pointer. It's quite a good one. We sort of define a term, a soft mem leak and a hard mem leak, and I'll go into what those are later and how we use them. And of course, all the old ones you'll see in Canvas today use write fors from the heap algorithms themselves. And this is sort of how you do that. You have the debugger sort of tracing the allocations. you have your reverse engineering process, understanding the complete architecture of the program, and you sort of dissolve the program into a collection of heap manipulation primitives. And of course, understanding the heap algorithm, and there's some really good papers on this, and we just touch on it briefly here. And this is the look side, which is a sort of little mini cache. And the free list, which will look like this, and you can come back to this later. And the sort of chunk coalescing where they combine two chunks to make one big free chunk, which is useful. And of course, you want to know when they split the chunks. And the reason we sort of abstract this is because not every program uses, in fact, many don't use the Microsoft heap at all. Mr. Esser over there was talking about how Zend invented their own heap algorithm, which is perfectly okay. And now they've added specific checks into their heap algorithm to sort of duplicate the work that everyone else has already done in the standard heap algorithms. So these techniques are applicable to both the sort of default heaps on various architectures, but also the specific heaps that Random Bob, the big programmer, thought he was cool enough to invent all by himself. So we have, as part of our development process, and if you're looking at it from an economic standpoint, we usually invest between 1 and 6 months in writing a good heap overflow, which means we believe our heap overflows will last for the conceivable future of a product. So before the overflow, the heap is in a state. And what you see in a lot of bug track postings is people assume that the heap is in a stable state. But that heap, not even the most perfect heap overflow, is going to work on more than 80% of the machines. Because the heap on my laptop, for some reason, is always different from everyone else, and vice versa. So assuming that you have some understanding of a heap, and it's in a default state, people have connected, deconnected, the freeze, mallocs have happened. The overflow occurs, corrupts memory, and there's then a write for, and Nico has this in quotes because write for may not necessarily be a write for. Any memory access will do, hopefully a memory write. And of course, typically we then use a function pointer, and there's some great features in ImmunityBugger for finding the function pointer that is used after you've corrupted a heap. So you corrupt the heap, you type bang func pointer, or I think pointer mod, or he named it something funny. You hit enter, and then you run the program some more, and it tells you when the next function pointer is hit, because you really want the very next function pointer. And the way he does that is modify all the function pointers to be 1, 2, 3, 4, and then wait till the access violation happens, which is simplistic but good. And of course, you also have to survive your payload running. And in Windows, this is exceptionally hard because many of the APIs use a or the heap you're corrupting. So lately, we've had a similar level of success by corrupting cryptographic tokens instead of doing function pointers. And this is us trying to defeat the DEP and the NX bits. Because sometimes all you want to do is make an Xbox or an SBox turn into a bad SBox, something perhaps a bit more trivial, crackable, and then log in. Because if I can log in, I can log in, and I don't have to worry about DEP. So that's certainly one angle that I think you're going to see a lot more of in the future, and I believe David Litchfield's giving a talk on that tomorrow, sort of. So assuming you understand the algorithm, the first step of any heap overflow is to fill the heap holes. And we have a cute little animation here and a little vulnerable function. And this, in effect, is the exchange X link state vulnerability done right. You can make it quite reliable. So assuming that the free list has there's a chunk missing out of the contiguous chunks, it's a little bit fragmented, and then you do allocate, and then you fill that in, and you do another allocate, and it'll allocate it from the end of the memory section. You do your overwrite, and you've overwritten something that you have no idea how big is and what it has. So in terms of predictability, you have really none. But in the past, in many cases, if you look at sort of advisories, and like my old paper, we ignored this whole problem. So in order to solve this problem, to make the heap overflow predictable, we need to find one of two kinds of memory leaks, which is I want to be able to tell the program to allocate memory and not free it. And I can do that either in a hard way, which means typically it's a bug in the program. This is the sort of thing that programmers are really looking for, which is something that will remain allocated forever, essentially. They've lost it. And the other thing is a soft memory leak. And these are much easier to find, almost as useful. Often they have a timeout that restricts you. So on this, like if you're hacking China or something, then your exploit will fail because you timed out and it got free. But assuming you're not, memory leaks that are often there because you just connected multiple times. So I know that I can fill up memory just by connecting 15 times. And if you're looking for hard memory leaks, the typical one is when they raise exceptions and they just forget to free memory. And this is the sort of very primitive abstraction of what the vulnerability was. You would say, I want you to allocate 400 hex bytes, and then you would say, here's the last one, and it'll free that. So given that we devolve the algorithm into just allocate and free, and we make, I think, 3 connections, and in 2 of them we allocate, and the other one we free. So we empty the data, and this realistically is very specific to the Microsoft one, but works just as well, slightly differently to the sort of proprietary allocators you'll see in all sorts of software. So this is what we really want to do. We want a mem leak, and we want to fill that little chunk, and we know exactly how big we want that mem leak to be, so we want to be able to specify the memory size. We then want to let them allocate twice and then do the overflow. So this is still very timing dependent, because if someone else is allocating and freeing on the side of us, they may interrupt our process and otherwise piss us off. And of course, here is the next stage of our lives, which is getting a function pointer working. So we call it intelligent debugging, the sort of process where you're creating essentially a script to do your debugging, and you have a much greater wide area of knowledge about what the program is. You're no longer just x/2iing. And this is essentially, that was our, many years ago, our project plan. We're like, what are the requirements for our new debugger? And this is what it looks like. You can do all these things now. Many of these scripts are Nico's work. You can dump the heap the same way you could in WinDebug. So if you're used to writing your heap overflows in WinDebug, which used to be your only real option, then you will feel at home. And that was our goal, because we've been teaching classes for a long time on how to do heap overflows, and we wanted all the class material to still work perfectly well on the new debugger. And it looks like this in a teeny tiny little font, and you can of course replicate this in your own copy of Immune Debugger. You can search it. There's a little scripty language, so if you want to search the heap for various things, then you're like, this is where you're answering the questions that you have in your head. You're like, what block on the heap is exactly 768 bytes? And then it pops out. One important thing that you're not going to get realistically with a normal debugger that is not sort of vulnerability focused is being able to sort of corrupt the heap and sort of snapshot and restore the heap structures so you can see what happened. So this is a really useful feature if you're doing some of the more complex heap overflows. We also do sort of the flow of a rather large chunk of the program, sort of a feature of the program. I want to know how that affects the heap in a general sense, and we call that heap fingerprinting, heap fuzzing. And you can fingerprint the allocation pattern and find double frees quite easily and that sort of thing. And mostly I look for mem leaks using this. So that's sort of automated. You go, oh, well, I'm at the stage of my exploit where I need a mem leak. All right, let's go. And then instead of spending years looking for one, it just tells you that a heap was freed but not allocated, and then it detected a mem leak, and this is the data that was in the mem leak. So right away I know in my packet what it was that filled that memory leak, and I can start adjusting the size and seeing how big I can make it and how small I